If you are on the YouTube channel right now, live studio audience, you'll want to please mute your computers. Otherwise, we're going to start hearing me in echo, and one of me is more than enough. All right, we're looking at Unit 8 right now, and it starts off with 2D areas. 2D areas, it's just a bunch of formulas right now. So it's all about what kind of shape, and then you match it with your formula. You'll want to get these formulas memorized before you go into taking your TSI. So those of you who have not done your TSI math yet, they don't give you these formulas. So my recommendation is, as you're practicing this unit, that every time you come across it, you rewrite the formula each and every time so it sticks in your head and you can use it whenever you need it. Okay?
I finished the TSI in like 5 minutes.
You finished it already?
It was like 20 minutes.
Yeah. Some people can get there real quick, and that's fine. But there's the geometry portion may have you do areas and stuff. So here are the formulas. Perimeter, just add up all the sides, and that's what the formula that you see there.
Oh, I see the one for triangle.
Yep, there's the one for triangle. 1/2 base times height. Now the trick with the base and the heights, and you're going to hear that come up a lot: base times height, base times height, base times height. They have to be 90 degrees to each other. So it doesn't matter which segment you call the base and which segment you call the height, as long as they're 90 degrees to each other. Which means in that triangle, if I really wanted, I could call that blue line, the dotted line, I could call that the base. And I could call the red line the height if I wanted to. It doesn't make sense, right? Because the line that's blue is inside the triangle. And you can't sit a triangle on something inside of it and then have it measure how tall it is. It's weird. Yeah, so B would be the base, H is the height. And so the way I've highlighted in the diagram makes sense. But I say this because you need to keep in mind that those two things need to be 90 degrees. So look for that right angle marker. Perimeter of a square, just add all the sides. Area of a square, it's the side length squared. Here we have our parallelograms. Rectangles are parallelograms. So they're going to share an area formula. You would have seen area formula for rectangles length times width, right? But now that we are all grown up in geometry, we call it base times height. But it does the same thing. In parallelograms, base and height look different. Take a look at that screen. Base is red, height is blue. And I've put the right angle indicator in yellow so that you can see it. If you've got your notes out, please annotate your notes. Use color. And when you're working on Delta Math, TSI, the Eduphoria test you're going to take toward the end of the year here, coming up in about a month and a half, like really soon, you can look back at your notes, and I would recommend that you redraw the figure you see on your screen and then color on it. Here's area for trapezoid. Trapezoid has two bases. The bases are the parallel sides. So whatever sides you were told are parallel to each other, those are the bases. You're going to add those together, and that sum is what you multiply to the height. Again, you want something 90 degrees to both of the bases. And then that result, you're going to divide by 2. It says multiply by 1/2. Divide by 2 is the same thing. Questions on parallelogram or trapezoid area formulas? I'm going to check the chat. Thank you, S4M, for saying that this was amazing. If you're in the room, thank you very much. If you're watching live, thank you very much. All right, let's look at area for rhombus and kite. A rhombus is a parallelogram. All the 4 sides are congruent to each other. The D's in this case, ladies and gentlemen, are the diagonals. And this is where geometry and math can get confusing for a lot of folks, is that we've used this letter D 3 different times in just this year alone. The first time we saw it, it was distance. The second time we saw it was in circles, and it was diameter. And now we're seeing it with rhombus and kite, and it is diagonal. I'm sorry that all three of those words start with the same English letter and that we're using the same letter for all of them. So context matters when you're picking your variable symbols. The reason why we're multiplying the diagonals together and it's not called base and height is because, again, you want things to be 90 degrees to each other. And in a rhombus and in a kite, the diagonals are 90 degrees to each other. Questions on area of rhombus or kite? Fabulous. Take a quick look at some examples. Here's examples of finding area of a couple different shapes. I've already worked those out for you. Let me zoom in on 1A. Yes, absolutely. If you'll also turn off the light switch closest to the door, it's causing glare on the iPad. Perfect. Now the stream doesn't have a horrible glare. Read what I did here. I'm going to give you about 30 seconds to read my work. I'm going to make one adjustment, bless you, for something that I saw.
I'm thinking about if it could be broken down or not. I mean,
2 and 9.
that's what I was
Yeah.
thinking. 2 and 9.
All right. What questions do you have on any of my writing up there? And it's okay for you to say, Miss, what does this symbol or what does this word mean? Because you didn't understand my handwriting.
2. Not could be broken down at 2, 3.
Yes. And there's your pair.
Oh, okay. I think I understand now. So
All right. So it all makes sense?
got it.
Yeah. It's all good? All right. Let's look at 1B.
So this will be for me.
There's my work for 1B.
Okay.
Ten, if you want, you can log into YouTube to that channel I put up at the beginning. Oh, you've got it. You are the one that's watching. Okay. You're watching too? Nice. Why does it say Pythagorean triple next to the 25 feet? Why would I write that? Is that a burning question you have? Anyone? Matthew? Is that your burning question? Why would I write Pythagorean triple? Like, what is that? Is that your burning question? A little bit, because you don't remember what a Pythagorean triple is. Yeah. And it's okay to admit that. Nothing wrong with it. Ask the question. Ask the question, Matthew. You can do it.
What question?
Why did I write Pythagorean triple? Or what is a Pythagorean triple? Those are two good questions. Or you have another question. Ask the question. Do you know why I put Pythagorean triple? Is that your question then? Sure. So ask it. Why did I put Pythagorean triple? I put Pythagorean triple because that's my rationale as to why I said that this particular side length right here, that is 25 feet, I'm saying that I got it as 25 feet using the Pythagorean triple. Pythagorean triple is any set of 3 whole numbers that satisfy the Pythagorean theorem, that a squared plus b squared equals c squared equation. That white triangle has a right angle, which means it's a right triangle. And at the time, I only knew that one of the sides was 7 and the other side was 24. I'm looking for the hypotenuse, the side directly across from that right angle, the one that I've labeled as 25 feet. If I had put 7 into either A or B and 24 into either A or B and solved it, I would have seen that 25 is the number that I have to put into C to make that equation true. But I didn't go through that lengthy process of substituting and squaring and adding and taking the square root and doing all the algebra stuff because I have my Pythagorean triples memorized. I know that 7, 24, 25 is a Pythagorean triple. Check it out. I'm going to go to Google and I'm going to search for Pythagorean triple. You can tell I've searched it before. I'm going to click on images so it brings up a whole bunch of them. And I like this one. And look, there it is. I highly recommend that you find one of these graphics. This one's my favorite because it's colorful and there's not much going on. And copy this into your notebook. Or print it out if you don't feel like writing anything and you have access to a printer. Print it. You have a bunch of empty pages at the back of your book. Make a tab on one of them labeled Pythagorean triples, print this out and glue that onto that page. Did I answer your question? Does anyone else have another question? Even if it's a miss, what did you write on the second line thing? Y'all can read my horrible handwriting? I've trained you well. All righty. Here was me calculating the area of the trapezoid because it talked to me about this tote, this purse, and it was in the shape of a trapezoid. So I identified the bases, I identified the height, I shoved them into the formula and used a calculator. Here's an example with a rhombus or a kite. I'm not really sure. But because they told me that this was either a rhombus or a kite, they used the same formula. So I just grabbed my formula. I identified my diagonals, multiplied them, and called it done. Same thing with this shape. Moving on, the hard part about this unit is that regular polygon. In particular, its area formula. You can think of this area formula in one of two ways. Both of them have the half. Both of them have the A that stands for apothem. I'm not trying to say opossum like a taquach with a lisp. I'm saying apothem. Okay, that's a TH sound. It's a segment that you draw from the center of a regular polygon and it's perpendicular to the side of the polygon. It also ends up being the perpendicular bisector. So it's going to cut that side into 2 equal pieces. So that's what the A stands for in these formulas. The top one is N times S, N being the number of sides and S being the length of the side. But if you take the number of sides and you multiply it by the length of the sides, that gives you the perimeter of the polygon, yes? So you also see this formula written as 1/2 times the apothem times the perimeter. The formula is not complicated, but what makes it hard is there's potentially trigonometry involved. So you get a second shot at some trigonometry. Here's my color coding of that figure. I'll pause here for just a moment in case you want to color code that figure for yourself. Notice the apothem, the blue one, the A, goes from the center of your polygon out to one of the sides, hits the side at a 90-degree angle. S is the length of that side, and P is the perimeter all the way around. All right. I'm glad I muted the mic for that announcement.
I'm missing one of them.
And then with the area addition postulate under your chair, which allows you to add up pieces of a shape, you can start finding area of composite figures, areas of things like this. And the trick with composite figures is to find smaller shapes that are easy for you to recognize. So parts of circles or a square or a trapezoid or a triangle. And you cut the shape into those pieces, find the areas, those pieces, and then add them back up. All right. Here's example 3 in your notes. Formula for a regular polygon. First thing I needed to do is I needed to identify what regular meant. Equilateral, all the sides are the same. Equal angular, all the angles are the same. Hexagon, 6 sides. I then looked at my shape and I went, okay, I need to find one of the measures of this thing. So the first thing I did here in this corner was I found the measure of that entire corner of the hexagon. I used my polygon angle sum, the number of sides minus 2, that times 180, all divided by the number of angles I have, which is the same as the number of sides, 6. When I calculated that, the hexagon's angle is 120. Do you see that line from B to C, which is the radius of our polygon? That bisects the corner angle. So if I look at that triangle, there's a 60-degree angle in that corner. I've got 90 in the other. That means that top angle there at B is 30 degrees. Questions on how I did those calculations? Okay. I have only the side length of 3 meters, which means that little tiny triangle that I traced in black, that side length there is half of the polygon side length. So that little piece from D to C is 1.5. So I drew that triangle out a little bigger for myself over here so that I could look at it. So 30, 60, 90 right triangle. I've been given the measure of the short side. I can use my special right triangles to avoid more messy Pythagorean theorem. And I found the length of B to D, which was the apothem and the only length I needed. I did not care about the hypotenuse of this triangle. Now that I have that measurement, I went into my area for a regular polygon. I put area, capital A, really big, and then subscript. I give myself a symbol or an abbreviation of the thing I'm working with so I know what area formula I want, especially since the number of times in a day that I get interrupted, even by my own thoughts, is scary. So the RP in this case stands for regular polygon. So area of regular polygon equals 1/2 apothem times perimeter. I just calculated the apothem, And then I found the perimeter as 18 because each side was 3 and there's 6 sides. 3 times 6, 18. I shoved that into a calculator. And you see the squigglies? There's 2 squigglies, one on top of the other. That's an equal sign that got all kinked up. Because if the lines are straight, it's exactly equal to. If the lines are all kinked up and squiggly for the equal sign, yeah, it's an approximately. You're right. So the area of this regular polygon is approximately 23.4 square meters. Which means if I needed to paint this and I was going to the paint store, if I look on the label of the paint cans, it'll tell you how many square meters or yards or feet or whatever that you can cover with this paint can. And so I would just need to make sure that I buy a paint can that is at least that amount. Preferably more, because then I can do multiple coats. I'm going to zoom back out so you can see the whole thing. Oh, and I did use a calculator. There we go. Hopefully it's still big enough for you guys to can see. Those of you who are in the classroom but you're watching on YouTube, how blurry is like the screen, the writing? Because on my screen, on my preview, it looks really clear in the center, but on the edges it gets kind of blurred. Is that what's happening with you guys?
Yeah.
That is happening, but it's not too bad. Okay. Okay. I don't think I can zoom in on this webcam. I'll have to switch it out for one of my webcams at home.
You can just put it closer now.
Yeah, but then you can't see the whole iPad. And then I have to remember where I'm zooming, and that gets crazy. All right. So that's how you would find the area of a regular polygon. And I can do that with any regular polygon. Here I did it with a triangle. I had to assume it was equilateral. And I did that with the square. And I did that with an octagon. With the octagon, I definitely had to use some trigonometry. So let me zoom out just a touch so that you can see all the crazy numbers that I put. Do you want me to talk through the trig portion? Yes. I heard a yes and I saw a couple of nods. Okay. So that trig portion. As I was looking at this little triangle right here, let me try to zoom in a bit and hold it. So as I was looking at this triangle right here, I noticed that I would have an angle measure of 67.5, which means this is not a special right triangle. So I can't use my 30, 60, 90 tricks. So I have to find some other way to solve it. And I only know one of the side links. That's the apothem link, the one in pink. So what I did was over here, I redrew the triangle, and I put a little colored dot where the angle was. And then I used that information with the side that I had, measurement of 8, and the side that I was interested in, which I labeled as X. And I tried to figure out which trig function I had the two sides representing. Because I don't have any information about the hypotenuse, nor do I care about the measure of the hypotenuse, I scratch out the trig functions that had the H for hypotenuse. So sine and cosine, out. Not invited to the party, go away. Tangent is the only one left to use. Tangent is opposite over adjacent. So I wrote tangent of the angle measure, which in this case was 67.5, equals the measurement of the side opposite that angle, H, divided by the measure of the side adjacent to that angle, X. And then I solved for X. Questions on the solving? Do you want me to talk through how I solved it, or can you see what I did? Sam, you want me to talk through how I solved it? Yeah? Okay. So we have our first line, the tangent 67.5 equals 8 over x. And I found that my variable x is in the denominator and I didn't want it there. So I had to get it out of the denominator. To get things out of the denominator, you multiply everything by that denominator. And so that got me the second line that says x tangent 67.5. That means x times the tangent of 67.5. Tangent is an action, so it's acting on the 67.5 and will give me some number that my calculator knows how to do, but I don't know, so I'll worry about it later. And because I'm trying to solve for x, and x now is being multiplied by whatever the heck tangent 67.5 is, if I divide both sides by that, I will find that x equals whatever I get when I take the number 8 and I divide it by whatever the tangent of 67.5 is, which according to my calculator was about 3.137. All right. Plugging that into my formula for perimeter, I found the perimeter was 53.02. I did multiply the x by 2 because remember that x was just that bit of the triangle over here. It was just that tiny little piece right here. And the whole side length is 2 times that. So I had to multiply it by 2. That's where the 6.627 came from. Now that I have the apothem, which was given to me, and I have the perimeter, which I just calculated, that's why we had to go through the trig thing, was I had to find the perimeter. Bless you. I now have the area of this regular polygon, which is 212 approximately 212.1 inches squared. I did not write the units. I'm sorry. Questions? Comments, concerns? Feeling better? Those of you who have already poked into the Unit 8 stuff on Delta Math, this is starting to get it to make more sense? Good. I think we'll do Unit 9 next week as a preview. Yeah? We'll do the same sort of thing? Okay. And then here's a composite figure below. I colored the 2 different shapes that I saw. I wrote down the formulas for each of those shapes. I plugged in the values I was given. If I had to solve for some values, I would have, but I didn't. And then I added it up for the grand total area. What makes the composite figures hard is it might not be obvious what shapes to cut it into. My recommendation, trace the shape onto some paper and just start cutting. I have tons of paper, and if I run out over there, just let me know. I'll find you more. Do all the cuts. Just. Area of a circle, unlike the radius was 2 pi r. The area is pi r2. But we need to talk about what a sector is. When we learned about circles earlier in the year, we talked arc length. And arc length was like the crust of the pizza. The sector is the area of that pizza slice. So instead of it being the crust, which is just like the line that goes around the circle, the sector is where all the toppings go. So it's the cheese and the sauce and the pepperoni and the mushrooms and the anchovies, the pineapple. Thank you for that look. I appreciated the pineapple on pizza disgusting face. Please feel free to start that debate in the comments. Keep it civil. The perimeter of a sector is the distance around the sector of a circle. So if you were, I don't know, putting ribbon around the pizza slice. I don't know why you would put ribbon around the pizza slice, but if you were, you would need to know how much ribbon, and so you would get the two radii that are the edges of the slice, and then the arc length of that slice. If you recall how you found arc length, which was to think about the ratio of the arc length to the circumference in proportion to the angle measure that's creating that arc length to the entire way around the circle. So that fraction equals fraction moment. It's the same thing for area of a sector. So the area of the sector of the circle divided by the area of the circle has to be equal to whatever measurement is of the angle that's cutting out that sector divided by the whole way around the circle 360. And if you put an equation form, it looks like that. I don't like using the equation form. I like using the proportion form because it gives me the freedom to find the area of the circle if I know the area of the sector, or to find the angle that it opened if I know the two areas. So just for me, it gives me more freedom. And here was me playing with area of sector. Questions? I found both the exact, leaving it as with the symbol pi, looks beautiful, and the approximate. And there's more examples there. I've already uploaded this as a PDF into Google Classroom, so you can read it from there. Okay? And here's composite figure, but this time with piece of a circle. .3D area gets a little wonky. You have to be able to identify the 3D object as opposed to the 2D object of square, rectangle, circle, sector. Now you have to identify the polyhedron, and they have cool, funky names. You have to be able to identify the face of the polyhedron, that is the flat surface. So if you think about this room being a polyhedron, a wall would be a face, the ceiling, the floor, those would be faces. An edge would be the line segment where those faces intersect. So it would be like the seam between the two walls, the seam between the wall and the ceiling. A vertex is the point where three or more edges meet. So like the pointy corner where two walls and the ceiling run into each other, that would be a vertex of this room. If the polyhedron has faces that are all regular polygons themselves, we're going to call the entire thing a regular polyhedron. And in three-dimensional space, that should give you pause. Three-dimensional space? Does that mean there's four-dimensional space? Five-dimensional space? Six-dimensional space? Yes, these are all dimensional spaces that exist theoretically, but we can't observe it because we're stuck in 3 dimensions. But mathematically, theoretically, we could talk about them. We can discuss them. We can look at the silhouette of shapes that would live in those higher dimensions and make some guesses from just their shadows. The same way that you looking at this 2D image of a cube, your brain is interpreting that as a 3-dimensional object, because I told you that those dotted lines were like you seen through into the back of the shape, yes? So if I told you that's a cube, that's a box, your brain knows to make it 3-dimensional, knows that you could spin it and look at the top and the bottom and the sides and all sorts of things, yes? Well, that's what some theoretical mathematicians do to look at shapes in the fourth dimension is they look at projections in second and third dimensions, what we're used to seeing, to try to figure out what the shape looks like in 4 dimensions, which is why we talk about polyhedrons of a certain number of dimensional space. In 3-dimensional space, there's only 5 regular polyhedrons. There's the tetrahedron with 4 sides, tetra meaning 4, hexahedron, or the cube, 6 sides, the octahedron with 8 sides. It's like 2 pyramids stuck together at the bottoms. A dodecahedron with 12 sides, and an icosahedron, bless you, with 20 sides. She's allergic to dodecahedrons. If you play Dungeons and Dragons, these shapes will look familiar to you as the base sets of dice. If you don't play Dungeons and Dragons, maybe let's do that during one of my mentoring days when we're not crazy busy with exams. Identifying whether things are polyhedron or not. Polyhedrons, again, going to have polygon sides. So cylinders, cones, spheres, not polyhedrons, because you got some curvy curves. All right. We've got prisms and cylinders. They're essentially the same thing. They're 2 congruent parallel bases separated by some sort of flat surface, usually parallelograms in the case of prisms, some sort of curvy surface in the case of cylinders that if you were to slice it and peel it open, like the label on a water bottle, it turns into a parallelogram. We have 2, oh my goodness, me not knowing how to use iPad. 2 kinds of surface areas you can talk about. Lateral surface area, those of you who speak Spanish, lado means the side surface area, and total is all of them. The sides, the tops, the bottoms, the all. Here are your formulas. I've put prism and cylinder together because the formulas are identical. The lateral surface area is you take the distance all the way around the thing, around the base, and you multiply it by however tall your prism stands. In polyhedrons, that distance all the way around is called perimeter. In cylinders, that distance all around is called circumference. And if you're going to do the total surface area, you're going to grab the side surfaces and add to it the area of the 2 bases. And again, since we're using base here to talk about an entire surface, we're going to capitalize it, so we don't get it confused when we're writing it with base times height of like a parallelogram or a triangle, which also uses the word base. So you'll hear me say the base face. So total surface area for a prism or for a cylinder is the lateral surface area plus both of the areas of the base faces. If you're handed a star formula chart, and there is no star for geometry, to be clear, but at once upon a time there was. And so the state of Texas created a formula chart for star geometry. If you're handed one of those, this is what those formulas are going to look like on that chart. Here's some examples that I worked out. The hard part is identifying the base. If there's any not parallelograms, it's those 2. If they're all parallelograms, then pick 2 that are parallel to each other and we're happy. And then total surface area, there was me calculating that lateral area, the area of the base face, and me just plugging in numbers and using calculator. Unashamedly using calculator to help me with the addition, subtraction, multiplication, division, because I'm very bad at that. Again, you'll find the PDFs for this on Google Classroom. Any general questions right now while you have me? Nope. All right. That ends where I was working on, but we'll keep talking. Pyramids, like the pyramids of Giza. Cones are basically circular pyramids. They have all the same stuff, slant. Okay, there's a difference between height and slant height. The height is how tall the thing actually is. The slant height is like how tall it is if instead of you went going straight up through the middle with like a rope, you leaned a ladder against the side of it and you tried climbing up the side. So climbing up the side is slant height. Climbing up a rope dangling from the very top is the height, the altitude. Do you get the difference? Okay. Here are your formulas. Because pyramids have this triangle feel to them, we've got that 1/2 happening, like we did with triangles. Again, the lateral surface area is the perimeter of the base, which for polygons is perimeter, and for circles it's circumference. And it's not height this time for the lateral surface area, it's the slant height. The distance you would be climbing up a ladder if you lean the ladder against the side of the pyramid. And the total surface area is the lateral surface area plus the area of the base face. And since there's only one base face, there's only one B. And it's a capital for the area of the base face. If you were handed a geometry star formula chart, that's what you would see. That's what those formulas look like. The cone formula looks way more complicated than it actually is because they actually put the pi in there. Oh, I did start some of these examples. Had to calculate the slant height because it wasn't given to me. And since I wasn't given angles, I was given just 2 side measurements. I used Pythagorean theorem. Simplified by hand, and then had my calculator give me a decimal because I wasn't sure which of the 2 I would need. And I drew out the little triangle. This triangle that's right in here. That slice. This triangle. That one that's like sitting inside of the pyramid. That's what's drawn off to the side. And then once I calculated the slant height, I threw it in, shoved it into a calculator, got an answer. You're at the point of the year where I've given you tons of tools. We have trig, we have special right triangles, we have Pythagorean theorems. And now you have to decide which of all those things you're using. There it is for a cone. Works exactly the same way. If I wasn't given the slant height, I'd have to calculate, probably with Pythagorean theorem or trig. Just depends on what information I have. Volume and cross section. Did y'all ever play that mobile game ages ago, Fruit Ninja? Some of you have. Some of you have not. Those of you who have, you know how you'd slice it and the banana would like open up into 2 pieces? And it would sometimes come and you could see like the round part of the banana. That circles the cross section. You have sliced into the banana. And you would get maybe ovals if you didn't slice it like perfectly right down the middle. But if you did it at an angle, it would turn into like an oval, right? Yeah. If you did it like perfectly, like long ways, you would get this crescent shape. I've never managed to do that. Take a look at these cross sections. And if you can read, you may have to grab your cameras to zoom in to next under the volume what I wrote. I'm going to answer this question here. All right, so if you think about these cross sections, so my Fruit Ninja players, imagine you took that watermelon and you sliced it, but you sliced it a whole bunch of times and you made those slices like super, super thin, like the thinnest sheets of paper ever. Okay. And then you restack those slices back on top of themselves. Wouldn't you get back the whole watermelon? Can you see it, 10? Okay, 10. You use the imagination. Picture watermelon. Picture slicing watermelon to paper thin slices. Now stack all those slices back on top of themselves in the order you cut them off. You have watermelon again, yes? With perhaps less juice than the first time. But it's still watermelon. That's volume. And if you look at the formula for volume of a prism, that's essentially what that is. The area of the base times however tall the shape is. And now you're at the point where the formula you use for area of the base depends on the shape of your base. So you're going to have to look at whatever shape base you have. This one's a triangle. This one's a circle. Your starting formula for volume stayed the same. Volume equals area of the base face times the height. But the formula you use to calculate the area of the base face depended on the shape of that base face. Pyramids are going to feel the exact same way, except for some reason it's a 1/3 instead of a 1/2. I still haven't figured out a good reason why it's 1/3 instead of 1/2. I think it has to do with something in calculus. Those of you who go on to take calculus 1 and 2, can you come back and explain it to me? Thanks. If you're handed a geometry star chart, formula chart for some reason, that's what they'll look like. And again, these I think are posted or will be posted soon to Google Classroom. We have spheres. Here's the formulas for sphere, surface area, and volume. There's only one variable in here. That's the radius. You know the radius of your sphere, you're done. Again, I don't know why it's 4/3. I suspect it has something to do with calculus.
For surface area,
Yes.
you have a correction that I got from Ms. Martinez that it's supposed to be 4 pi r squared.
Oh, yes. 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 It's pi r squared. Thank you. Typo. Fixed the typo in your notes. I had a typo. That should be pi r squared in the surface area, not pi r cubed. I mean, that's Unit 8 in a nutshell. The only thing left to talk about is symmetry. That's where you can fold things. But I've been yammering on more than long enough. I'm going to leave you now to work on practice things. please feel free to ask me questions. Thank you very much.